right, streaming is on, and we'll go ahead and get started. All right, so I'm guessing that all of you guys know that Canvas is asking you to, if you want other people to learn how to pronounce your name, you can do a voice recording of your name, how you want it to be pronounced, and apparently that would be appearing somewhere within the people link in the class. So just an option. I mean, if you guys want to do it, go ahead, and if not, you can just ignore that. This is relatively new too, because I used Canvas yesterday and it wasn't there, but it's here today. All right, so let's go ahead and get started with this class. Are there any questions about the homework assignment? No questions?
Wait, are you going to show us the results? The solution?
Well, that's kind of what I'm asking. Do you guys have any questions before I?
Yeah, I mean, I'd like to see if I did it correctly.
Oh, okay, sure. We'll do it that way. Yeah, so that's typically the way I would like to do things is, in the class, I want to give you the solution of a previous homework assignment. The assignment is due at 6 p.m., which is just 2 minutes past. So this is a perfect time to do that. And I'm going to use exactly the same instructions to do it other than the uploading part. I have LibreOffice already installed, so that part, I cannot, I won't do here. Besides, it's Windows, and you guys are using Windows, I'm using Linux, so, or Mac OS, maybe using a Mac, but it won't work in this case. But I can replicate this part here. So I'm just going to download trace nested as a file, and I'm going to download it in the same file name as what you would. So save it, replace the file that I already have in place, and then I have to use LibreOffice to open it. Okay. Did anyone have any problem installing LibreOffice? No? Okay, good. All right, so inside LibreOffice, I'm just going to go to the folder where the file is downloaded. And it should be here. There we go. All right, so once I open it, in class I have to kind of zoom in a little bit because otherwise it's kind of difficult to read. And then I use Window, New Window, to open up another window so I can do the trace while displaying the source code. And I'm going to zoom in this one a little bit too. The zoom control, by the way, is all the way down here. So if you want to control the zoom, it's over there. Yep.
One problem I had with LibreOffice when I got to this part was it seemed to be actually auto-updating the first window I had open when I updated the second one. Do you know what needs to be done to prevent that?
Well, it is the same document. Of course, it's going to update the first one.
Well, yeah, but I mean, normally when I'm coding, I want to see the old version in another window next to the current version. Is that possible?
I think you are not using the different tab because you have one algorithm tab and one trace tab. So if you're working with a trace tab, it should not interfere with the algorithm tab.
I'll look at the tabs next time.
Okay, all right. All right, so first thing first, in the trace tab, let me double check and make sure that if we are streaming. So, okay, we are streaming, audio is good. All right, so the first thing we need is a line, number, column. And then we have comments because we do have conditions to evaluate on line 3 as well as line 5. And then we have to have one column per variable. We got variable x, variable y, and also variable z. And those are the columns that we need to set up. X, Y, Z don't need that much space, so we can shrink it if you want to. There we go. Comments I think that's probably sufficient. And then line number can also be a little bit shorter. I suspect this one is going to be long enough where I need to scroll one portion. So I'm going to use this to control that, to make 2 panes so I can scroll one pane while maintaining the other one as the header. All right, so we'll go ahead and start tracing this code. The precondition is, in this case, we don't really need to know anything about any of the variables, so they can all be question marks. Okay, now we start with line 1. Line 1 initializes x to 5, so we put the x 5 here. So with a normal assignment statement like this, you do not need to put anything in comments. If you do, that's fine. I'm not going to take any points off. It's just that it's not necessary. Yep. Oh, okay, I thought that's a question. So on line 2, we are initializing y to 0. Oops, line 2, y is 0. Question?
Oh yeah. So what if I didn't put the pre-line? Does it matter in this one?
Then you get some points nudged.
But you didn't give us nothing to put in there, so I just.
What?
Since there was no values to start with, I just didn't think that.
But you need to tell me that there are no values to start with. That's how we communicate that you do not know anything, or it is not important to know any specific value for the variables. And this has always been the way that I've done it in class.
No, I know. Yeah.
Yeah. Okay. Okay. So now we evaluate whether x is greater than 0, and it is true because x has a value of 5. 5 is greater than 0 is definitely true. So over here you can spell out true, or you can just like me, use t instead of true, because that saves some typing. Yes. That's fine. Yep, as long as it is clear. Okay, so we go to line 4, because line 3 is true. We go to line 4. Line 4 initializes z to 0. And then we go to line 5. Line 5 is asking the question, is z less than x? So the answer is true in this case, because x is 5 and z is 0. So now we go to line 6. So nothing should be really tricky at this point. Line 6 is just adding 1 to z. So z increments from 0 to 1. Then we go to line 7. Line 7 is adding 1 to y. Y goes from 0 to 1 as well. And then at this point, we have to go back to the beginning of the inner loop. The beginning of the inner loop is on line 5, so we need to go back to line 5. Re-evaluate, is z less than x? The answer is it is still true, so now we have to do it again. Go to line 6 again. Increment z, so z is now going from 1 to 2. Go to line 7. We're adding 1 to y, goes from 1 to 2. We go back to line 5. This part is fairly boring. Okay. You can definitely copy and paste. Now, if copy and paste is what you want to do, then you want to specify that this is whatever this value is plus 1. And then you look at this one, you specify this one as the previous value plus 1. Okay. Now copy and paste truly works. Okay, I'll show you. Yeah, go ahead.
I know it's a bit redundant, but would putting line 8 and just making the comment that it just makes a loop of the process, like is that docu points, or would that just be excess information? I mean, like, is it wrong to put line 8?
In this class, when we trace, we are tracing every single line of execution. So we do not, shortcut it and go like it's going through X many times, and as a result.
I mean, like after 5, 6, 7, could you put 8 and then put the comment that it's like add n while, then check, go back to 5?
He's talking about the end while statement itself.
Oh, okay. You can include that. It's not a problem. Okay, see how when I paste, it automatically updates to 3. And then 4. This is not cheating. It's called working effectively. It's improving efficiency, right? I mean, but the question is, when do you stop? Do we stop now? Is this my last iteration?
No, go one more.
We have to go one more. Because, we have to wait until variable z has a value of 5. Then 5 is less than 5 is false, okay? So this time when we go back to line 5, xz is less than x is false. That is the reason why we continue to the line that is after and while, which is line 9. Okay, so this is one of the more important transition. So I can highlight it. So we'll just highlight these two rows, just because it is kind of important. Okay. Okay. So when we get to line 9, there's not much to do. X just gets x plus 1. So x gets x plus 1. Oh, x. Okay, fine. Minus 1. Thank you. Okay. I didn't even read my own code, right? Okay, so line 9 is subtracting 1 from x. X is now 4. And then we go back to the beginning. So we go back to line 3. And line 3 is re-evaluating x is greater than 0. And that is still true. And then we repeat the whole cycle, almost. Okay? So what are we going to do? Well, we can kind of copy and paste it. Okay? But then you have to find out where to end. So copy and pasting is not necessarily saying, oh, okay, this is just cheating, and as a result of doing this, I would be understanding the algorithm any less. If anything, it is actually understanding the algorithm a little bit more, because now you have to think, well, how much should I copy and paste? Because it's not the whole thing. If it were the whole thing, well, I mean, it's not very educational anymore. But since it's not the whole thing, it is actually more useful. So if you look at this code here, the terminating condition has to do with whether x is greater than z. Okay, or if when x is greater than z, we continue in the loop. So that means this time will terminate when x has a value of 4, because now x already has a value of 4. So that means when you copy and paste, you kind of have to be careful which part you copy and paste. This is the portion that we can copy and paste, but just a copy and paste is not going to work either, which means even though copy and pasting is really helpful, but you can see how the values of z is okay, because z is reinitialized on line 4, so it gets reset to 0. But y is not. Y is only initialized once on line 2, and we do not reset the value of y after this. So that means y is not going to reset to, it's not going to increment to 1 from 0. It's going to increment from 5 to 6. Okay? So that means, but in this case, because I use a formula the whole time, or almost the whole time, I can now just say that this is 5 plus 1, and the rest is now automatically updated. Kind of cool, huh? All right, so we are now back to the point where variable z now has a value of 4, which means we are going to exit the inner loop. So now we exit the inner loop. That would go back to line 5 first. Re-evaluate the condition of line 5. Z is less than x is now false. And then we go to line 6 now. Line 9, excuse me. We go to line 9, and we decrement x one more time now. So if I use that method consistently, so I just say it is this number minus 1, and that will lead us back to line 3. But line 3, we have done it already, so we copy and paste again. But once again, it is important to know how much to copy and paste. So we should only copy and paste up to here. Okay, so copy, paste. But every time after I copy and paste, I would actually double check. Okay, so I look at line 9, goes back to line 3, go to line 4, reinitialize z to 0, go to line 5. Okay, so everything kind of checks out, and now this is going back to line 5, where z is less than x is false. Then we go to line 9, we decrement x again, so x is now 3 minus 1. So you can see that if you use copy and paste, it's not quite as painful, but otherwise you just kind of have to do it by brute force. How much time did it take you? I can actually tell when you turn in the file, because it will tell me how much time you actually spend on the file itself. So if I see everybody spending like 15, 16, 20, 22 minutes, and then one says 5 seconds, then I go like, why is it 5 seconds? Why is it so different from the rest? Note that this has nothing to do with how smart a person is, because even with all the copy and pasting, it's still taking me quite a bit of time. So the only way to do it in 5 seconds is copy and paste the answer from somebody else. All right, so getting back to line 5, the condition is false. To line 9, so we're almost there. It's now 2 minus 1. And then we go to line 3 again. So we look at line 3, and this time we only copy and paste up to here. Like so. And we get back to line 5. The condition is now false. We get out. We go to line 9. X is now decremented from 1 to 0. And we are not done yet. We still have to go back to line 3 first to reevaluate that x is greater than 0. It's finally false. Then we get to post, and we're done. So it's a little bit long, 70-something lines. Yep.
When we post, do you want the values across the bottom?
No, because the assumption is if a particular cell is empty, then you just look up to the most recent update to find its current value.
If we put the values across the bottom?
That is not a problem. Yep.
Alright, so do I get points off because I forgot to put true or false?
Hmm?
Do I get points off because I forgot to put true and false?
You will get points off. Because the whole point of comments is to document what the condition, how the condition was evaluated. Was it true or was it false? Because whether it's true or false determines where you should go next. So that's the whole reason why we kind of keep track of that in the comments column. All right, so are there any questions? Did you guys all get to 15? No? Where did you guys get up to? Something other than 15. There are a lot of numbers other than 15. Yep, okay. Well, it's your first homework assignment, so don't take it too hard. Okay? So don't take it too hard. I just, it's 5 points, of this for this particular homework assignment, but in terms of proportion of the entire semester, it's not going to be that much. All of the homework assignments add up only to 20% of your final grade. So I wouldn't, be too upset, if the homework has a few points, knocked off, or even if the whole thing is, get a 0. Okay? But I would spend the time to figure out why points are, deducted. That is the important part. Because the idea is you learn from your homework assignments so that you don't make the same mistakes in the exam. Is that okay? Yep, go ahead. It will be when it's done, when it's graded. Yep, because it's just, due in 20 minutes, it's not automatically graded. I haven't figured out that part yet. Trust me, I will work on it until I get it. Yep.
So if this assignment's worth 5 points, then if somebody makes a small mistake, then you take a fraction of a point off.
It's going to be a fraction, yeah. So what I usually do is I break up the 5 points into a rubric, into multiple criteria in a rubric. So one rubric may be, saying, okay, do we have a precondition? One rubric may be asking, do we have the right columns? One rubric may be asking, is there indication that the trace indicates understanding of how an algorithm works? Another one may be whether the trace indicates understanding of how a loop works, when to stay in the loop, when to exit of a loop, and so on. So each one has its own point value, and each one has its own scale that goes from 0, which means there's a lack of indication or it's completely wrong, to full scale, to a full mark, which is, okay, this is perfectly done, I get everything that I need. And also somewhere in between, which is like, well, it's for the most part right, but something is not right, okay? Yeah. So that means, depending on what is missing or depending on what the difference is, the deduction can be very minor, can also be kind of like a major deduction if it is a conceptual thing. Yep.
So for the trace table,
Uh-huh.
on
It will be just like this in an exam, except I will give you paper that's already lined horizontally. So you might want to bring a ruler to provide a vertical ruling. So that kind of makes sense, right? Because I don't want to give away how many columns you will need by giving you the vertical ruling, but then I will give you the horizontal ruling so that you don't have to, so that things won't skew out of place so badly that I cannot follow it. Is that okay?
So your exams are on paper, not on Excel spreadsheet or whatever?
The exams are face-to-face in this classroom on paper. No electronics, but it's open book and open notes. Now that is a big thing, okay? So you might want to keep that in mind, because if you already know the exams are open book and open notes, anything that is either handwritten or printed prior to the test. Sorry?
What book?
What book? Whatever book you can find. Doesn't even have to be related to this class. If anyone wants to bring in some holy scripture of whatever religion, I'm okay with that too. That does not bother me at all. If you think that's going to help, bring it.
So this is sort of unrelated, but for the rest of the classes that you teach, are they all open book, open note?
Yes. So the first exam, second exam, and the final exam, they're all open book and open notes.
The other classes that you teach at this college?
Yes, they're also all open book and open notes.
Do I say then you're not so scary?
That depends on how you look at it. Because what it means is, I do not ask memorization questions. And it also means that if somebody, forgets one particular symbol, what it means, during the exam, I cannot answer the question. Because if it's open book and open notes, then it is actually your responsibility to bring the material with you. If you think something is going to be helpful, bring it with you. But I cannot answer questions like, oh, what is the definition of this thing again? I didn't bring my notes. Okay, in that case, I cannot answer that question. Okay, yep.
And then last question, the time, so 2 hours, 1 hour, half an hour?
That I have not decided because I don't want to use all 2 hours for the exam for 2 reasons. One, you guys will be very, very tired. Okay, and 2, I will run out of time for lecture as well. So my current intention is to only use 1/2 of the class for the exam and then the other half to go over the exam or on new material, depending on a few other factors. So I'm leaning on only a 1 hour exam instead of a 2 hour exam. Because the final is 2 hours. But I don't want the midterm 1 or exam 1 and exam 2 to be 2 hours as well. I have not decided yet. A lot of stuff usually is to be determined in my case. Have you guys made your personality test? Have you taken the personality tests? Mm-hmm. Okay. So did you guys read about what perceiving means in the last letter of a personality type? Okay, so the last letter is J versus P. People with a J as the last letter means they have a strong sense of how things ought to be. So they are the planners. They are the ones who have to be prepared for everything. They are the ones who have everything laid out in plans. And when you go to their houses, it's well organized. Okay, everything has a place to go. Perceiving P is exactly the opposite. And guess who I am? All right. So I'm assuming the homework is okay at this point. I know it is a little bit tedious, okay, but it's really just to get you guys warmed up to the whole process of tracing like this. I promise you in the exam it's not going to be this tedious, okay, because tedium doesn't really help me understand whether you understand a particular concept or not. It only shows me how fast you can write, which is not the point of this particular class. Agreed? Unless you guys say, but I really want to show off how fast I can write. All right, so I'm going to put this aside for now, and then we'll move back to the notes that we have been working on since last Friday. This is why I like Monday, Wednesday, Friday classes, because we don't lose track of the context too quickly in this class. And I just have to kind of get rid of some of my other tabs that I don't need. And there are many of those. Oh, I think I just got rid of one that I should not. But that's okay. You know, we are back on the slide that we were talking about last time, pre and post conditions. So I'm going to go back to the table of contents and just kind of get a quick review of what we have already talked about. So we have already talked about constant assignment. We talked about resolving references to variables to constants, simple self-referencing assignments, the forget operation, and conditional statements. So we got through all the way to section 3.5 already last Friday. Okay, I'm hoping you guys got a chance to at least review the material and then think about it. So do you guys have any questions up to section 3.5 in this particular module? Or anything that's related. It doesn't have to be, you know, a particular thing, but it just has to be like, you know, something related to pre and post conditions. Yep, go ahead.
When writing actual code, how often should we be doing test cases for like pre and post conditions to test and see whether or not it's mathematical?
That is a very good question. Okay, so the question is, in actual coding, okay, in commercial coding, how often should you consider pre and post conditions? Would that summarize your question?
Yeah.
Okay, so I want to point out one thing in actual real programming. I can pick out a programming language, let's say C++, okay? And it has a feature called assert, okay? So let's look it up and, you know, just quickly find out what it is. And, okay, this is a little bit small. We'll expand it a little bit. Okay, so here we go. So assert is a particular, it's not exactly a function, but it is, you know, something that you can add to your code. And you can assert what we call an expression. And guess what? This expression is either true or false. So basically, you can sprinkle assert statements throughout your program, hopefully at very critical places. And you basically say, at this point, this condition really should be true. Okay? So what happens is the program can do, or your program after compiling can do runtime checking. So every time you specify assert something, okay, let's say x is less than y, okay, it will be evaluated right at that on that particular line. And if the condition that you specify in assert is false, then your program is going to throw an exception, which basically translates to it's going to quote unquote crash out. But it doesn't just crash out with nothing. It crashes out with a message that says on line blah blah blah, the assert of this expression is false. So that means, you know, if you analyze the pre and post conditions, not for the entire program, but just use the method, and you go to certain really critical places and go like, at this point, you know, this particular number really should be less than that number. You put that assert in, and if for whatever reason your program has a flaw that ends up with that condition being false, then the program is going to, you know, exit, but with a very informative message that says on which line which condition has failed. So that would give you a chance of catching programming flaws, not analyzing the entire code, because, you know, analyzing hundreds of lines of code is already really, really time consuming. But the method that we use in this class can give you a good handle on, you know, I think this condition really should be true at this point. Make sure that that is the case. So is that kind of answering your question?
Yeah.
Okay. And assert is not unique to C++. In Java, in many other programming languages, they have similar features, so that, you know, the programmer can put in checkpoints to make sure that the code is sane. And if it is not, okay, if it doesn't do what it's supposed to, then you can catch those mistakes earlier before the program does something that's damaging. Okay, so that's a good question. I like that question. All right. I'm just going to close off some of these extra tabs. And all right, there we go. So now we're going to go on to the pre and post condition analysis of loops, okay? And this is going to be a little bit more difficult compared to a conditional statement. The difference between a conditional statement versus a loop is, in the case of a loop, things can be done in a repetitive fashion, as opposed to, oh, we just do it once, either on this branch or on the other branch, okay? So the post condition is a simple or between the post conditions of the two branches. That's relatively simple. But when we get to loops, then we have the pre and the post conditions forming a loop. So that becomes a little bit more difficult to analyze. So what we'll do is I'm going to start up the tablet. And, okay, is that kind of fun? Okay, I'm not sure whether you guys can read it or not. There's a Luke Skywalker here, is Sith tolerant, and then the program is called Jedi. That's what we do in cisp 440. I have no idea why people think it's a difficult class. All right, so we'll go ahead and start up the tablet. Okay, there we go. And we'll start with just a picture of a loop itself without even specifying the conditions. So we have a incoming path, and then we have another path that's coming in. Then we have a little post here that is asking a particular question. I'm just going to use C to represent the condition. So C is an expression that evaluates to either true or false. And then we have two ways to proceed. There's a branch here, a fork. One fork says, if C is true, we go this way. The other branch says, if C is false, then we go the other way. There's some kind of statement that we need to execute here. Okay? And then we go back to the earlier point. This is a pre-checking loop. And then the false is going to get us out of here. Okay. So I think we kind of know this picture already. Okay? We have used this picture before. Except this time, what I'll do is I'm going to put some line numbers and some code next to it. So we have line 1 being the while loop thing. So I would just say while C, do the following. And then line 2 is going to be responsible for the body of the loop. And for the lack of a better way to describe it, I'll just say it's a statement. Okay? So line 2 is the statement inside the loop. And then line 3 is end while. This is the end of the while loop. Of course, this is not an actual program because I'm not telling you what condition to evaluate, and I'm also not telling you what statement I'm executing as the body of the loop. So this is only used to give you a sense of the structure of a loop. Okay? You have a condition to evaluate. If the condition is true, we perform an operation. After we perform the operation, we go back and re-evaluate the condition. So we keep doing this until the condition evaluates to false. Then we get out of the loop, and then we continue with whatever is after the loop. So are we doing okay so far with that? So the problem with this has to do with the post condition of the statement somehow becomes a part of its own precondition. You go like, what? Well, let's go ahead and look at this. So I'm just circling this cross section here and ask, what is this condition here? Well, I cannot tell you because I don't know what statement is on line 2, and there's no way I can actually tell you what the post condition is. That's fine. We'll just call it post 2. Okay, because it is the post condition of line 2. And then it goes all the way back, so you can see how it goes all the way back to the beginning here. And if the condition is, if condition C is true again, then we get back to here. So now the question is, how would I write this line here? Well, if you want to know what is this line, it is obviously called pre2 because it is the precondition of line 2. It is the condition right before we execute line 2. But what is that? Well, we know two things. Okay? We know that in order to get here, the condition C has to be true. Okay. So part of this precondition is C itself has to be true. But there's a little bit more to it. What else do we know? Now let's also circle this cross section here, and we'll call this pre1. In other words, before we even evaluate the condition the first time, pre1 is known to be true. Okay? So now looking at this picture, what else do we know as a component of pre2? We know the condition has to be true, because otherwise we wouldn't stay in the loop. But we also know that the following has to be true. It is an OR statement, because we know we cannot differentiate. At this point, we cannot differentiate. Is this the first time we get into the body of the loop? Maybe. Or is this the second time or the later? Maybe. So now we end up with something like that. Okay, let me move this up so I can actually close the outer parenthesis. There you go. Okay. So do you see how the analysis of pre and post to can be a little bit messy because it is based on itself and something else? Is that okay? So what do we do to deal with this? That's the next question, because we have a circular type of reasoning. How do we figure out what is pre-to or post-to when it relies on itself? Well, maybe we need to look at a more concrete example. So that's what we'll do next. So we'll keep this slide around. Okay, I'm starting a new slide. And on the new slide, we'll just go ahead and say on line 1, we have x gets 0. On line 2, we have while x is less than some k. Okay, I'm not even telling you what k is. On line 3, we have x gets x plus 1. On line 4, we have and while. Okay, and we're going to use the picture, a pictorial representation. Okay, so the first thing is just x gets 0. It's only executed once before the loop. And then we specify the loop. So because it's a pre-checking loop, there's a way to merge back into the branch here. And then we ask the question, x is less than k, is it true or not? Based on that, we might want to get out of the loop. Okay, that's the false branch. Or if it is true, then we want to stay in the loop and perform that one single operation, which is x gets x plus 1. After we perform that operation, we just go back and reevaluate the condition. So I'm just basically redrawing exactly the same trail map as last time, except that this time we have C being a concrete comparison. We also have statement being a concrete assignment statement. Okay. All right. So how do we analyze the pre and post conditions in this case? What do you think is appropriate of pre-1? If this is your entire code, okay, what do you think is appropriate for pre-1? Pre-1 is true. Very good. And why is that? Why is that appropriate? Exactly. We have, first of all, we do not have any other variables, so there's nothing to say. But even for x, we don't need it to start with any particular value, because the first thing we do on line 1 is to overwrite it. So pre-1 is true. Okay. And then what is post-1? Now, you have to remember which rule to use here. So every time we deal with an assignment statement, we have to choose either to use a substitution rule or a forget rule based on the function of the right-hand side of the assignment statement. So in this case, the function to the right-hand side of the assignment statement is simply 0. In other words, f of x equals to 0. So the next question is, does it have an inverse? Yep. No. It does not have an inverse, because it will map every single value of x to a 0. So knowing that it has a value of 0 after the operation does not give me any information to reverse back to what it was before the assignment. Yep. So we use forget. Very good. So we basically say we forget what we already know as pre-1, but we don't have to forget everything. We just have to forget everything that we knew about x. And after that, we can also say that, oh, after this, we also know that x now has a value of 0. Okay. And once you expand it, you go like, oh, what are we actually dealing with as pre1? Oh, that's easy. Pre1 is just true itself. So it becomes true and x equals to 0. And that just becomes x equals to 0. Well, wait, hold on. How is this happening? How can we claim that true and blah, blah, blah is just blah, blah, blah? How do we know that?
True doesn't represent any actual condition.
That's not the reason. Do you guys remember what a truth table is? Okay. Well, there are two items that makes this work. Okay, so I'm going to use maybe just this area here to illustrate that rule. Okay, so when you look at a truth table, okay, we have x. Okay, let's not use x because it coincides with the name that we are using. So we use a and b. Okay, so we have a, b. A, b are independent variables, which means the value of 1 does not change the value of 2. They are not related at all. But both have to be Boolean. In other words, what does it mean when I say a is a Boolean variable? Does anyone want to kind of explain what that means? Go ahead. It has to be either true or false. Okay, so the either or is actually used correctly in this context. It cannot be both. Cannot be neither. It can only be one or the other. Okay, but that applies to a as well as b. So that means when a is false, b can be false. But when a is false, b can be true as well. What about when a is true? Same kind of scenario. When a is true, b can be false. When a is true, b can also be true. Is that okay? So these are the 4 possible ways to combine the values of a and b, assuming a and b are independent variables. If they are dependent, then the table may not look like this anymore. So a and b being independent is a very important point to make. So now we just say, okay, well, if that is the case, what is a and b? Okay, it's the same way that we use the word and in English. False and false is false. False and true is false. True and false is false. How about the last one? True. Oh, that's the only time it's true. Okay, so now what we want to do is to look at this truth table, and then we go back and look at the pattern here. So this pattern says the first one, or whatever is to the left-hand side of the conjunction, is true. And then we got something that may or may not be true to the right-hand side. So do you think, which 2 rows do you think it matches in the truth table? It matches 3 and 4. It matches these 2 rows. Okay, so I'll go ahead and focus on these 2. Okay, and we say, all right, so what is so special about these 2? Do you see how the value of b is also the same as the value of a and b? Yes? So that shows, that proves, okay, that definitively proves that true and whatever is just the whatever. Because we have shown for all possible ways to arrange the second, or the value to the right-hand side of the conjunction, true and whatever is just that whatever. Okay, so this is how we prove certain axioms and definition and theorems in Boolean algebra. Now this class is not focusing on Boolean algebra. There will be another class to do that, but these techniques can be very useful because this is a very, very useful technique to understand Boolean expressions. So are we doing okay so far with this? All right. All right, so that means I can make this particular jump here to basically say that, oh, post 1 is just x equals to 0. Okay, not really surprising. If that is the case, what next line, what other line should I analyze? Yep. Mm-hmm.
We have to go through all the forget for post 1.
Yes, so mechanically you have to go through all the forgets, because in this particular case the forget has nothing to forget because there's nothing that I have stated in pre-1. But what if this loop is not on line 1? What if this loop is on line 216? And there's a whole bunch of stuff that we know already prior to the execution of the loop. Because what we want to do is to find a mechanical method so that we can apply that, without having to use our mind to think about things too much to do the analysis.
So up to this point, we haven't been forgetting post one. We haven't been doing the forget operation on post.
Oh, we have been doing the forget operation. It's just that there's nothing to forget when we perform the forget operation.
So I copied your notes pretty closely.
Uh-huh.
I've not gone through the forget operation on post one. This is the first time that I've seen this.
To see.
So, in other words, usually you just say post one equals or is or whatever word x equals 0.
All right, let's go back to the notes. I'm pretty sure earlier, okay, we have, okay, so if you look at this part here, and we want to look at post 2 and post 4.
Okay, so does that apply just for loop statements?
Nope, anytime you have assignment statements where the right-hand side does not have an inverse, you use forget.
Okay, so we need to be forgetting from line 1 all the way down if it doesn't have an inverse.
The forget operation only, okay, so let me go back to the tablet here. So in this case, the forget operation is only forgetting everything that you know about x. So it's not forgetting everything. It's only forgetting things in pre-1 that mentions x. So you have to look at what is pre-1 and find out, okay, did we claim that we know anything about x in pre-1? In this particular case, it did not mention anything about x. So the result of forget is the same as before we forget, because there's nothing that mentions x in pre-1.
So I'm absolutely not trying to argue with you. I just know that
That's fine.
when we went through section 3.2, when we started on line 1, you gave us a precondition, and as w is less than z, and then x equals 0, and then for post 1, you just said pre-1 and x equals 0. So should we have forgot?
Yes, we should have used the forget operation, which was what we did on Friday.
Yeah.
Yeah, the notes is a little bit more simplified.
Just a little bit. That's all right.
Okay, all right. All right, so we are getting back to the tablet here. All right, so what we have now figured out is this is basically post 1. There we go. And pre-1 is this part here. So if I want to draw a cross-section and say that what condition is at that cross-section, pre-1 is true, which is here. And then post 1 is x equals to 0, which is here. So are we okay so far? Okay. All right. So now we have to get into the tricky part. Because the tricky part is we also want to know what is the condition here. What is post 3 in this case? So post 3 in this case is, well, we kind of know what to do with this one. Okay, because what we do is we completely forget that this is inside the loop. And we just look at line 3 and go like, what is line 3? Line 3 is an assignment operation. If you look at the right-hand side of the assignment operation, if we say f of x is x plus 1, does it have an inverse? Can we reverse that operation? Yes, we can. What does it look like? What does the inverse look like?
Negative f of x.
X minus 1. Okay, so f inverse x is x minus 1. So then we know which rule to apply. Which rule should we apply in this case? The substitution rule. Okay, so we apply all of that analysis, and then we say, yeah, we know how to do it. Post 3. So post 3 is using the substitution rule on pre-3, and then we look at every occurrence of x and replace it with f inverse of x here. Now I'm just going to be more specific. So f inverse of x is really just x minus 1. And that's it. So we go like, yeah, we can figure it out. We just need to know what pre3 is, right? As soon as we can express what pre3 is, then we can just go ahead and replace every single x in pre3 with x minus 1 in parentheses, and we're done. Sounds pretty easy peasy. Yep. Because line 2 is a very tricky one. So we'll get back to that one, okay? When we try to compute when we try to figure out what is pre3, then we'll integrate line 2 into the whole thing. So right now we're just focusing on line 3 because what we know, this portion here is only dependent on line 3 itself being an assignment operation and that the right-hand side has an inverse. That's all we need in order to come to this point. Okay? So now we look at pre3 and go like, well, since this post 3 depends on pre3, then we'll go ahead and try to figure out what is pre3, what is the precondition of line 3. So this is where we encounter a problem. Because pre3, okay, just like the previous slide indicates. Okay, let me just kind of go back to the previous slide for a moment here. So in pre3 of the new code is pre2 in the old code. So in the old code, it integrates 3 components together. One component is the condition of the loop itself. One component is the precondition of the loop itself. And the other component is the post condition of the same statement. Okay? So we're going to copy this pattern to the new one. So when we copy this pattern to the new one, then pre3 is, okay, remember the condition of the loop? If the condition of the loop is not true, we wouldn't be here to begin with. So in this case, the loop says x is less than k. Okay, we'll put it here. And then we have a disjunction on the other side. Because one has to do with, what if this is the first time ever that we get to line 3? Then the precondition is really just the precondition of the entire loop itself, which is post 1. Okay, so I'll just write down post 1 here. On the other hand, if this is not the first time we get to line 3, but we have gone through at least one iteration already, then we also have to include post 3 as a part of this expression. Is that okay? Let me color code this, okay? I think color coding would help here. If anyone is colorblind or has sensitivity to certain colors, let me know. Okay, so I'm going to color code what part is contributing to what. So the red line of x is less than k is needed in order to take this branch here. The blue part, which is post 1, basically means this is the first time we get into the loop, so we are coming straight from the precondition of the entire loop. And then here comes the green part. Where's the green? Green, green. Oh, right there. Okay. So the green part is the post 3. This is where we say, oh, this is not the first time we get into the loop here. And that's the green one. Is that working? Is the color coding helping? Okay. Cool. This is how my brain works. Power Rangers just popped up in my head. Yeah. Well, we are lacking pink and yellow at this point. Okay, so but that makes pre3 and post 3 kind of difficult to analyze because one depends on the other. If you cannot figure out what is pre3, then we cannot figure out post 3. If you cannot figure out what is post 3, then we cannot figure out pre3. They have an interdependency. Uh-oh, we have a problem. Okay? So how do we solve this problem? Hmm? there's only one variable in this entire program, and that's x. Yep. But you cannot just isolate x out because because of the pre and post condition thing. So we're looking at the before and the after effect of statement 3. What do you think? Yep.
If you can find post 2, that's pre-3, and then you can use that.
Okay, well that's a good idea. So if we can find out what is a condition so that pre-3 and post-3 can be the same thing, that might work out, okay? But that's not going to work because if they are exactly the same thing, they cannot be exactly the same thing because x is substituted by x minus 1. So any mentioning of x in pre-3, is going to be replaced by x minus 1, which means pre and post 3 cannot be exactly the same thing.
Didn't she say though to go back to post 2?
Hmm?
Move to line 2?
Say that one more time.
If you could find post 2,
Mm-hmm.
that would be pre-3, right?
Post 2, okay. So we want to look at post 2. So post 2, in this case, is the condition that is true here, which is the same thing as pre-3. So we would express post 2 exactly the same way as pre-3, which boils down to exactly the same problem that we have now. Because it's not changing the relationship between the conditions, we're just relabeling the conditions. Okay. So now we have to understand the concept of a loop invariant. Okay, so the one condition that has to be true in both in post 3 and also pre 3 is called a loop invariant. Okay, so what does the word invariant suggest? Okay, so I'm going to write it down here so that you can see what it looks like. Invariant. What do you think it means? Okay, so we'll pick out certain portions of this word first. What do you think vary mean? Change, alter, and stuff like that. Okay, what happens when we add the word in front of something? It's negated. Okay, so invariant it's basically saying something that does not change. Okay, it's constant, exactly. So a condition that remains the same throughout the entire thing. So this is the most difficult part of analyzing a loop has to do with this. It's called a loop invariant. Okay, there's no mechanical method to derive the loop invariant. It's basically just based on experience and quote unquote guesswork and plug in to see if it works. Okay, so we'll go ahead and test a few things. Okay, so we'll say what if the loop invariant is x is less than or equal to k. Okay, so we're just saying, okay, what if this is the loop invariant? That this condition stays true the entire time. Okay, let's give it a try. Okay, let's see if it works. So the loop invariant will have to take the place of one of these components because it stays true the entire time. In other words, we are basically saying the loop invariant is true when we are here, which is pre-3. It's also going to be true here in post-3. It does not change. So are we doing okay so far? Okay. In other words, we are asking so we'll go ahead and plug in this into post 3 and see if that works. So now we are assume post 3 is x is less than or equal to k. Would that work out with pre 3? Okay, so now we plug in this into pre 3. Pre 3 has the Power Ranger color thing, right? Okay, so we just kind of plug in the only thing that is unknown. So I'll go ahead and do the whole thing. I'll just copy the original thing first. Okay, this is post 1 or, oops, I shouldn't start to spell the word now. Okay, So pre3 is now x is less than k, and post 1, we already know what it is. Post 1 was, we figured that out over here. So x equals to 0. And then post 3, we don't know exactly what it is, but we have a wild guess. Okay, we're just kind of guessing that it is x is less than or equal to k. Okay? Are we doing okay so far? And now we look at this and go like, how is this helping us? Now, I forgot to specify one thing up at the top. So I forgot to specify that x is greater than 0. Okay, k is greater than 0. All right, so when we look at this and we combine the fact that k is greater than 0, what can we draw as a conclusion? Well, first of all, is there anything here that is kind of redundant and we don't really need that anymore? Yep. X is less than k. You mean the one on the outside? Yeah. Okay, yep, I think that makes sense. Does everybody see why we can just kind of remove the x? Well, that is the one that we cannot remove, okay? Not yet. Let's look into this part first, okay? It says x equals to 0 or x is less than or equal to k. Is one of these things actually not needed?
Yes.
Which one?
Since you defined x as 0, you could just make that just 0 and the rest of it.
But it's inside an or, okay? It's inside a or. So
X less than k, we don't need it because k is positive.
okay, all right, so yeah, go ahead.
If you combine things that x is less than k and x equals 0, can you just say 0 is less than k?
No, nope. Question? Yeah, go ahead.
Can it be x equal to 0 or x is equal to k, all candidate where
Well,
x is less than k?
let me just pull that component out, and we'll try to answer the question. So we are focusing on just this part, okay? We're just focusing on x equals to 0 or x is less than or equal to k. And, okay, one more thing that we also know is that k is greater than 0. Okay, so that's also a critical part. Yep?
Well, if we know that k is greater than 0, 0 is the cutoff. So x equaling 0 doesn't matter because it can be x or anything less, or it can be 0 or anything less than 0. So the x minus, or the x minus, or less than or equal to k is the only real thing that needs to be kept with the k is greater than 0.
That is correct. Okay. Go ahead.
Same.
Okay. We have a little bit of a.
Because as
Who-
I told you, because x is positive, and
Yep.
we have x equal to 0,
Yep.
it means x equal to 0 and x positive, k positive always true.
Mm-hmm.
And the statement depend on x less than or equal to k.
Yep. Okay, so how do we look at this from a number line perspective? Okay, because sometimes something visual is going to be helpful. So we draw a number line, and we just pick one spot to be 0. We pick another spot to be k. Is that okay? We know k is greater than 0, so it has to be on the right-hand side on the number line relative to 0. Okay, what about x? What is the range of x? Well, we know x has to be, it can be here because it can equal to k, but then it has to be less than or equal to k. Okay? So this is the range that is, or that's telling, this is the range because x is less than or equal to k. Okay? So we know this. We know x can be here and everything to the left-hand side. But we also know one more thing. We also know that x can be here. Don't we know that already? Because that point is to the left of k. Is that okay? So that means this part here is redundant. I don't need to specify that x can be 0, because by stating that x is less than or equal to k and that k is greater than 0, I already know that x can be 0. I already know that x can be -1. I already know that x can be -2, and so on. Is that making any sense? So if that is making sense, that means this entire expression is really just saying exactly the same thing as x is less than or equal to k. Well, of course, and on top of that, k is greater than 0. We don't need to know that x can be 0 anymore, because by knowing that x is less than or equal to k and that k is greater than 0, we already covered that. We don't need to say that one more time. Is that okay? Just logically, does it make sense? Yeah. Okay. How is that going to help us? Okay, so we have x is less than k because that only has to do with the other part. And now we simplify that. So x is less than or equal to k, and k is greater than 0. Something tells me that something here is redundant as well. What is redundant? Say that one more time. That's not the one that is redundant. So look at the number line perspective again. Okay, so we'll go ahead and look at the number line perspective. So this time we have an and thing, okay, which means we're looking at things that have to be true at the same time. Okay, k is greater than 0, so that part is still the same as before. This number line is still okay because we have one statement here that says x has to be less than or equal to k, but we also have another one that says that x has to be less than k. Okay, so that means, let's say k is an integer, okay? If k is an integer, then this is k minus 1. So that means we have another number line that goes like this. But we're only looking at the overlapping portion because the two conditions have to be true at the same time. X has to be less than k. X also has to be less than or equal to k, which means the equal to part is useless. Is that making any sense?
Because we've already defined that x is going to be less than k regardless.
Exactly. And it's inside a conjunction. So in a conjunction, when you have two conditions where one is more restrictive than the other one, then you can keep the more restrictive one and throw away the one that is less restrictive. In a disjunction, it's exactly the opposite. If you have one that is more general than the other one, you keep the more general one and you throw away the more restrictive one. Is that making any sense? More or less, maybe? Okay. Well, okay, let's say it makes sense. So we can now say x is less than k and k is greater than 0. Okay, so this is now pre-3. How is that going to help us with figuring out what is post-3? Because that's really, after all, what we want to figure out. Okay. I'm running out of space on this slide, so we're going to continue with another slide. So that means I'm going to put some extra information here and copy that to the next slide. There we go. All right, so now we can work on post 3. So we look at post 3 and say, well, I don't know, is this going to work out? Because post 3 is using the substitution rule. Whatever is in pre-3, whatever x is in pre-3, we replace it with x minus 1. That was the conclusion from the previous slide. Okay, let me just go back and tell you which part we're talking about. It is this part here. And that derivation only has to do with line 3 is an assignment statement. The right-hand side is reversible. That's the only reason why we come to this conclusion. Okay, so we look at this and go like, okay, well, let's give it a try. So we now expand what is pre-3. Pre-3 is just x is less than k, and k is greater than 0. And the rest I just copy. Now we actually perform the substitution. We see x here, replace it with x minus 1. So now we have x minus 1 is less than k. K is greater than 0 does not mention x, so we can just leave it alone. So we look at this and go like, how is this going to help us? Well, let's figure this out. So now we have, x is less than k plus 1, and k is greater than 0. That doesn't look like, the same post 3 that we were in our hypothesis. Wait, but there's something we can do here. Can I claim that x is less than or equal to k if I tell you ahead of time that x is an integer and k is also an integer? What do you think? So think about x and k only as integers. If they're both integers, and I say that x is less than k plus 1, does that really mean the same thing as x is less than or equal to k? Because it is an integer. Okay, so to understand this part, once again, I think a number line can be helpful. So let's say we draw a number line, and now we know that these are all integers. So we have one discrete point here that is k, one discrete point here that is k, one over here as k plus 1, okay? So to say that x is less than k plus 1 means the largest value of x can be what? It can only be k. What about k and a half? That wouldn't be an integer. Is that making any sense? The largest integer that is less than k plus 1 is k. The largest integer that is less than or equal to k is also k. So that's why this equality holds. So now we know that post 3 is the same thing as x is less than or equal to k. Was that kind of what we used earlier? Oh, so we have found our loop invariant. Post 3 like this is a loop invariant. It does not change. Is that okay? Wait. But that means we can now figure out what is the post condition of the entire loop. Okay, maybe we should take a 5-minute break first. To be continued. So we'll take a 5-minute break. We'll come back at 7:18. Yep.
What's your channel again for
making sure that we are still recording. Yep, we're still good. All right, so now let's go back a few slides. Okay, so we're going to go back to the general description here and go like, well, we're going through all this trouble, but the only one thing that I want is the post condition of the entire loop. That's the only thing that I really need to know. In other words, this is the bottom line that I need to know. And what is this? This is post 3. Okay? So how do we figure out what is post 3 in this particular picture where I don't even know what C is, I don't know what statement is, but just using post 2, pre 2, pre 1, and C, how do I express post 3 in this case? So we have to think about the ways we can end up at post 3. Okay? So let's try to use the Power Ranger approach again. Okay? But this time we're going backwards. So we look at this red line here and say, oh, okay, this is one way to get there. It's completely bypassing, you know, the body of the loop, the statement, and we just go straight from pre-1 to post 3. That's one way to do it. And then we use Green Ranger to indicate the other line. So Green Ranger says, nah, we did not come from here. Instead, we came from here. Do you see how the green line is? So the green line, you know, if I just want to add additional arrows just to emphasize that it is only going in one direction, and the same thing with the red line. Okay. So both the green or the red ranger can end up here. But when you're standing here, you do not know which line you used to get here. Yep.
Post 3 be either post 1.
Be very careful when you use the word either.
Post 3 would be post 1 or post 2.
And there's one more thing, because in order to end up here, they both have to take the false branch. So what do we know about C? C has to be false, okay? All right, very good. Okay, so now we know, C has to be false for sure, okay? But we also know that it can come from either direction. If it comes from the green line, then we know that post 2 in this particular picture is one component. But it may bypass one, an entire, the entire loop and not perform one single iteration, in which case it would also be pre-1. So this is a simple or, it is not an either, because we cannot guarantee that only one can be true. We'll just say that it is an or. Is that okay? Now this has nothing, absolutely nothing to do with the statement itself, or the condition, or the precondition of line 1. This only has to do with the structure of a loop. Okay? This is an abstracted version of what we want to do. So now we look at this and go like, okay, so how do we apply this to the concrete example that we are trying to solve? So let's go back to the concrete example. So it's a huge mess here, right? And we're interested in this line here, which is post 4. So we ask, okay, what is post 4? Well, based on the analysis that we have done before, we know the condition of the conditional statement has to be false, which means x is less than k has to be false. And then on top of that, we know that it can be the post condition of line post 3 in this case. So post 3 is assumed to be x is less than or equal to k, seemed to work out really well, with the pre and post 3 thing. Or it can also be coming straight from, let's see here, post 1, so x equals to 0. And on top of everything else, we also know that k is greater than 0, so that part is always there. Are we doing okay so far with post 4 being having those components? Okay. So now we look at this and go like, well, that's a pretty big mess here. does it even look like it can be true? Because it looks like we have some contradiction going on here. Because on the outside, we have a negation of x is less than k, and then on the other part of the conjunction, we have at least one component saying x is less than or equal to k. That seems completely conflicting. So what we'll do is we'll go ahead and analyze this whole thing. So we say, well, okay, let's take a look. We know how to simplify this portion, right? Because the x equals to 0, we know it can be simplified out. And we also know that it is not the case that x is less than k. It's really the same thing as saying x is greater than or equal to k. So now we say, oh, okay, x is greater than or equal to k, and x is less than or equal to k, and k is greater than 0. You look at this and go like, that looks kind of like a contradiction, which means it is something that is not possible. But is it? Yep, x equals k will meet that requirement. Because one says x is greater than or equal to k, the other one says x is less than or equal to k. Oh, when x equals k, both are true. Oh, okay. K is greater than 0 is just always there, so we'll keep that. So now we know that x is k and k is greater than 0 is our post condition. Done. So when we exit the loop, we know one thing for sure. X equals to k. Not greater than, not less than, exactly k. Is that okay? More or less? Okay. So I wasn't, just making a statement when I said, what is this crazy math? That's why this first section of this module starts with that. But when you think about it, did I talk about any type of calculus kind of math? No. Did I talk about any type of linear algebra kind of thing? No. So the math that we did use is just comparison and algebra, okay, and a little bit of Boolean algebra, but not a whole lot more than that. It really has to do with looking at the effect of statements and try to figure out if we knew before this statement this is true, what can we possibly know after this statement executes? And we extend those concepts to control structures. A loop is a control structure. A conditional statement is also called a control structure. So are we doing okay so far with all this stuff? Yep.
How did we come to the invariant exit?
You basically have to kind of guess and then plug it in and see if it works. So we just kind of make the assumption. That's why I use the word assume here. We say, okay, well, let's assume assume post 3 to be this, and k is greater than 0, and then we plug it in and see if it works. Now, most of the time, you can kind of guess what the loop invariant is based on the condition of the loop. So in this case, the condition of the loop is x is less than k. So the loop invariant usually has to do with the condition of the loop itself. So it has to include the condition of the loop and one little case when you exit the loop. So now the question is, when the loop exits, how would it change the condition of the loop? Is it equal to, or is it greater than? So you just kind of nudge the condition of the loop itself a little bit, to get to the loop invariant. Okay, that's a very good question. So there will be classes as an upper division class at a 4-year university. There will be classes that will talk about this sort of thing in details. So you will learn. What I did was to spend about 2 classes, okay, maybe 3 hours or 4 hours or so on this topic. This is one entire 3-unit class as an upper division class at a UC. Okay. So in this class, I just give you an exposure. But at a 4-year university, they will treat all of these topics with even more formality. but not all universities have that particular class. So some universities have that and some do not have that. All right. I can hear some relief, when I say, okay, we're done with this. This part, I think, I'm trying to formulate what I want to say. It's really set apart different branches along, a computer programming or computer science career path. If you find the topic that we just kind of talked about, the proving of theorems and stuff like that, if that is what energizes you, it really points out, one path is more suitable for you. And if you look at this and go like, okay, I want to, finish this as quickly as possible and not to look at it again, that really points you to a different path, in computer science, in all the different careers. It's not like, one is better than the other one. It simply means that, it is a divide, and whether you like this topic or not can help you decide which path you might want to pursue. All right, so we are moving on to a new module. It's called Top-Down Design. And we have touched on some of these topics already before. And we'll start with some real-life examples of top-down design. Okay, so there's a lot of text here, which is kind of boring. So I will start with something that you probably have some experience with already. How many people have taken English Writing 300? Okay, many people have. So how long is your paper, like the final project that you have to turn in? 500 words?
No, 5 pages.
5 pages. Okay, so typically how many words does it translate to? Sorry? 2,000-ish? Okay. So let's say you have to write a 5-page, 2,000-word, essay on some particular topic. Do you just sit down and start typing right away and write the entire thing from start to finish in one single session?
I'm a procrastinator, so that happens.
I can already kind of guess your personality type. Well, I'm kind of the same way. Yes?
Do you do your research and then, basically make
Uh-huh.
a roadmap to how you're going to create?
Ah.
That's how I want to do it.
Okay, very good. Okay, so you know what you're supposed to do. That's usually good enough, for practical purposes. Knowing what you're supposed to do is usually quite sufficient. That's the 80% versus the other 20%. So very good. Okay, so you want a roadmap, and a roadmap in terms of writing is kind of like just an outline. Okay, this is the introduction. This is the presentation of the raw information. This is the interpretation of that raw information. This is my conclusion, and so on. So you kind of have big topics. And then within each big topic, you can kind of break it down into smaller sections. So let's say we're talking about raw data. Okay, where did you get all the raw data? Well, I collected this information from this source, this information from this source, this information from that source. Within each one of those, then you present and go like, okay, from this source, I have collected information about this topic, about this, about this, about this. So you basically drill into the details, okay, as you work out the sections, okay. Other things that are quote unquote top down in design in real life is a tree. Okay, you go like, what? A tree? Yes, a tree. As in the kind of plants that squirrels like to live in. So we look at a tree and go like, what about the tree? Why does a tree have anything to do with top-down design? So I'm looking for a particular tree picture that, this one I think would do. So we look at this picture. I think that's an oak tree. Okay, so here's an oak tree. So what you're doing, or my point is, when you look at the main trunk here, okay, this is the main trunk, and you can kind of, it's countable how many branches is branching off of the main trunk, okay? I would guesstimate maybe 3 or 4, okay? And then you follow one of those branches. So let's pick up this one here. And at this particular point, it forks out, it splits into 2 branches. And if you follow one of those, it splits off into 2 branches. And here it splits off into 2 branches. Here, I think it splits off into 3 branches, and so on. So if you look at each junction, it's countable, okay, how many branches it splits off into. But if I ask you and ask, how many leaves are there in this tree? You go like, I have no idea, right? That is why we need top-down design. Because without top-down design, I'm asking you how many leaves is in this tree. But top-down design is saying, okay, so let's just say that each branch can only have up to 4, can split into 4 ways, okay? So now, can I point you to a particular leaf using like 60 words? Probably, okay? Take this branch and then follow this side, follow that 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 side. So you can probably locate one single leaf without overwhelming instruction. Is that making any sense? Okay? That is why we need top-down design, because we can only focus on so many things at the same time. That's the limitation of the short-term memory of people. Now, some people have exceedingly good short-term memory. They can probably keep track of more things than a normal person. But that is the exception to the rule. Is that okay? All right. So now we can get rid of this picture, because all it is just to explain the rationale of top-down design. So books are also organized in parts, and then parts into chapters, chapters into sections, sections into subsections, and so on. So that's why in real life we have a lot of things that are top-down. So now it moves on to in programming. Why do we have top-down design? Once again, we want to focus on just a few things to focus on. We just want to focus on a few things so that it doesn't overwhelm our short-term memory. You can look up, in psychology papers, like how many things most people can track in short-term memory. If you look at the phone number, that is a very good example. Okay, 7 digits. Okay, assuming the number is of the same area code that you're in, most people can barely remember 7 digits. I cannot even do that. So if I listen to a phone message and somebody is leaving behind a phone number, I usually have to listen to it 3 times to get all 7 digits. The first time I'll get maybe the first 2 and the last one. And then the second time I'll get the third one and the second last. And then the last time to get the actual digits in the middle.
And then you might have to do it again just to make sure you got it all right.
Exactly. Yep, exactly. So that really tells you about how many things we can actually pay attention to in actually focus on. So when we write programs, we also want to use the same approach. We want to look at the big problem and then go like, okay, we'll break it down into bigger chunks, okay? And we express how each chunk relates to another chunk. But we only want to look at like 5 or 6 chunks at a time. And then once that is figured out, then we go into one level deeper and go like, okay, this chunk is pretty big by itself. How do I break it down into statements that we can actually express in pseudocode? So that's the kind of general approach of top-down design. Is that okay so far? Okay. It's just really the rationale of top-down design. So in this case, I'll give you one example, of factoring. And we want to write an algorithm to factor a particular number into its prime components. That's all we want to do. And we want to figure out the pseudocode to do that. The first thing you need to do every time you want to write an algorithm is 1, make sure you understand the problem, okay? And 2, you want to know that you can do it by hand first. Does that make sense? If you don't know how to do it by hand, how can you write the instruction to tell a computer how to do the same task? So it kind of makes sense that we have to know how to do it. So the problem is quite simple in this case. We want to find all the prime factors of an integer, and we assume the integer is greater than 1. So we start with a particular assumption this time. So your precondition this time can start with something that you already know. So we want to do it by hand. So we look at an example of 20. So in this case, we look at 20 and go like, okay, what is the first prime factor of 20? Now, obviously, you don't have to start with 2. You can start with 5. You can start with 2. Those are the only 2 prime factors of 20. But it makes more sense to start with 2 because it is the smaller of the 2 prime factors. So you start with 2 and you go like, okay, 20 is 2 times 10. So you have now extracted 1 prime factor of 20. So now your new problem is, oh, what about 10? What are the prime factors of 10? So with 10, you say, oh, 2 is also a prime factor of 10. So you extract that. Now you have 5 left. And you ask, what is a prime factor of 5? Let's see. 2 is not, 3 is not, 4 is definitely not. Oh, okay, 5 is a prime number itself. And you're done, because once you factor out 5 from 5, then you're left with 1, and we're done. Is that okay? So with this example, we kind of get an idea of how to do it, but not really entirely. And why not? Because the example is so simple that all of you can just eyeball and say, oh, it's 2 and 5, done. You don't really have to go through a very systematic way to figure out the prime factors of a number. Is that okay? So this is one particular example that I want to show you. If you really want to force your mind to use a very systematic way of doing things instead of eyeballing something, this is how you do it. You give yourself an example that is not clear, that is not easy to solve. So you just go like that number, factor it. Now you're forced to use a systematic way to do it. Okay? Let me check whether we can use simple rules to do this one. So 8 plus 4, 7 plus 8, 2 plus 3. So we cannot use any actual very simple rule to do this one. Okay? So how do you do it? How do you find the first prime factor of this thing? You have to keep trying, right? You divide it by 2. Okay? I know it sounds really stupid to divide it by 2. And go like, what is the remainder of this number divided by 2? Non-zero. Fine. Okay. It's not 2 then. You divide it by 3. Non-zero. The remainder is non-zero. It is not divisible by 3. Can I try 4? In other words, if I try 4, can I possibly mistake 4 as a prime factor? It's not possible, because if it's not divisible by 2, it is automatically not divisible by 4. Which means if I divide this number by 4, the remainder is going to be non-zero. There's no way I can mistake this number as a multiple of 4, which means I can try 4. It's not going to hurt. It's just using extra execution time, but it's not going to hurt. I'll divide it by 5. You look at this and go like, Tech, I don't think you can try. You need to try 5 because the least significant digit is not a 0 nor a 5. But specifying those heuristic rules is actually not easy when you're programming, because the internal representation of numbers inside the computer is not in base 10. A lot of the rules of thumb that we already know only works because we're using base 10. Okay? That particular rule of, oh, if a number ends with a 0 or 5, it is divisible by 5, only works in base 10. If we're using base 2, which is what the computer natively uses, that rule doesn't work anymore. Okay? So a lot of rule of thumbs to us is a very it makes sense. It makes it really easy to test whether a number is divisible by another number. But it doesn't make sense when it comes to programming. What about 7? 7 is not that easy, right? With 3, we still have some rule of thumbs. You can add up all the digits. If the sum of all the digits is itself divisible by 3, then the number is also divisible by 3. But if you add up all these digits, it is not a multiple of 3. So we know 3 is not a factor. 5 is not a factor. What about 7? Well, you actually have to do the division to find that out, right? Okay. So now what you do, I highly recommend the use of a spreadsheet for this purpose. So what we do is we just do something like this. Okay, we just say, okay, this is a potential factor, and we are not even going to skip things. Okay, we're not even only doing prime numbers. We're doing all numbers. Okay, so we just go like, I have no idea whether that number is prime or not by itself. And now we just say, okay, give me the remainder. So mod is the remainder of a division. So we are now dividing this number by this number, and we want to look at the remainder. And we want to change this a little bit because we don't want the row reference to change as I copy. So we put a $sign here so that doesn't change as I copy the formula to the additional cells. So now I can use this. And oops, too much. Go back a little bit. There we go. So now I can, figure out, okay, do we get a 0 here? Not so far, I think. It's all 1, but we need a 0. So what we want to do now is to say, if this equals to 0, then we want to print found. Otherwise, print nothing. So this makes it easy to find out whether we have found it or not. Okay, and then we just copy this, zap through the whole thing. Whee! Okay, well, let's see if we can find the 0 or found. Oh, right there. So there's 1. Do we have an earlier one? Do we have another one? Let's see. Okay, so that's the only one. Huh?
What did you find? It's none.
Huh? What? I just randomly pick a number, that's all. In terms of personality type, this is what a person with a P as the end of a type would do. It's just pull a number out of thin air and go like, let's try this one. I know one professor who also sometimes teaches this class, but he definitely teaches, I think, cisp300. He can plan a lesson down to a minute. So at the beginning of a class, he would write down on the whiteboard and say, by 7:15, we'll be talking about this. By 7:20, we'll be talking about this, and so on. And I had the opportunity to evaluate his teaching. This is something that we have to do every 3 years. And he was actually able to follow that. Yeah, that's pretty amazing to me. I have no idea. I think he just kind of keeps track of how much topic he has to do and has a very good estimate of how much time it takes to go over a particular topic. He somehow can control the environment well enough to do that. So anyhow, we found our factor here. We found our factor of 379. That's pretty cool, right? But does it give us a does it give it an insight of how to do it in a procedural way, in a very systematic way? Kind of, right? I know this is not the smartest of all the programs because we are testing all the multiples of 2, multiples of 5, multiples of 10, and so on, all the ones that are obviously non-prime numbers. We tested those as well. But it doesn't make the algorithm incorrect. It simply means we are just wasting a little bit of processing time on things that really should not have been tested. But it doesn't make it wrong. Is that okay? So we now go back to this approach and go like, okay, so now that we have found that 379 is a factor, what else do we need to do now? Well, we just take the original number. Okay, so I have to find out where the original number is. is B1, okay? So we now say, okay, what about B1 divided by this factor? Okay, so now we need to factor this number. Does that make any sense? Because once we find one prime factor, then we have to divide the number by that particular prime factor, and then whatever the quotient is, we reapply the same technique. Is that okay? So now we look at this number and go like, what is a prime factor of this number? Then we do the whole thing again, right? So we start with 2. What is the remainder of this number divided by this number here? Oops. There we go. And we also have to make sure that the row number does not change as I make copies of this. And then the next row is just this number plus 1. And this one we can just drag it. And then we also want to specify, oops, too many times. So we also want to figure out whether we have found it or not. So we just say if this number is 0, then we say found. Otherwise, don't say a single thing. And copy it down here. And now we can take this. Whoops. Okay. So now we can take these 3 cells and make lots of copies of that. Like that. And I kind of know that I have too many of these already. So we should have found a prime factor by the time we get to a certain number. So even though I have no confirmation of a factor all the way up to 190, I can already make a conclusion that the number that we're dealing with is a prime number itself. In other words, I already know that 2,237 is a prime number. You go like, really? Can we make a conclusion that quickly? In fact, I will tell you that we have made a conclusion a little bit too late. I should have been able to make that conclusion even earlier. What is the square root of 2,237? Just give me an approximate number. It's less than 50, right? Because 50 squared is 2,500. So the square root of this number has got to be less than 50. Is that making any sense? Okay. So I claim now that all the numbers beyond this point is useless. I should have made a conclusion right there and say that, oh, that number is actually prime itself. Yep.
You should be able to factor it to test it up to 13 to find out if it's going to be prime, and if you hit 13, that's like the cutoff.
1,300 or 13?
No, if you can't factor it by the time you hit 13, that's like the cutoff.
No, you cannot guarantee that. Why do you think you can guarantee it?
Just from trying to remember factoring.
I don't think you can do that.
No.
Well, that's because I remove all the other ones. So once you remove a cell, the default value of an empty cell is automatically 0, so they all match. Get rid of those. Okay. No, we cannot stop at 13 because 13 is not quite at the square root of the number. Go like, but what about the square root of this number? Why can we stop when we get to the square root, when we have tested all the integers up to the square root of the number? Why do you think we can stop? It cannot get any higher. Okay, very good. So how do we express that in math? Okay, where's my, oh, right there, the little Android thing. Okay. So here's a theorem, which I'm not going to prove in this class, okay? But we will prove it in CISP 440. So the theorem goes like this, okay? If A is greater than or equal to 1, and B is greater than or equal to 1, and P is A times B, and we're assuming all the numbers are counting numbers, which means we're not dealing with fractional stuff, okay? Then the rule is to say that A has to be less than or equal to the square root of P, or b is less than or equal to the square root of p. Okay, so I'm going to say implies. Okay, this thing implies that thing. So whenever you think of a factor of a number, one of the because when you think about a factor, there's always a counterpart to that factor, so that the counterpart and the factor multiplies to the number itself. So A and B are both factors. So the theorem basically says if A times B is P, then at least one of A and B has to be less than or equal to the square root of P. Okay, so what you can do is to kind of think about it a little bit and throw some examples at it. Okay, so let's say P is, I don't know, 84. Okay, so I'm just thinking of 84 right now. So let's say P is 84. So you think of all the pairs of factors that can multiply, or where the product is 84. Okay, there are quite a few. So 2 times 42. 2 is definitely less than the square root of 84, I would assume, right? How about 3? 3 would be 28, I think. Okay, 3 is definitely less than or equal to the square root of 84, which is 9 point something. Okay, let's try 4. Okay, 5, nope. 6, yep, there's a 6. 14, what about 7? 12, right? There's no 8, there's no 9, 11, and then the next one is 12 already. So we're looking at the same entries, except they're listed backwards. So when you look at this table here, go like, oh, okay, the theorem seems to hold for this particular example. Now in this class, we're not going to prove the theorem to basically say it works for all examples of A and B and then P. Okay, but in the other class, in cisp 440, we'll formally prove this using a very interesting technique called proof by contradiction. But in this class, we just use the theorem and say that you only have to test up to the square root of a number. If you cannot find a prime factor up to the square root of a number, that number itself is prime. Okay? All right. So getting back to the spreadsheet, we kind of have an idea of how to do it now, right? Because I know this is a little bit excessive because I picked a number that has, the first prime factor is actually pretty big, but that's necessary, because if I pick 20, you can just eyeball and say, oh, it's 2, 2, and 5, right? But if I pick something like this, it forces you to actually try a systematic way and go like, okay, let's do it the long way, the more systematic way. So what is the systematic way telling you? Well, we can just maintain a potential factor, and then we divide the number n by the potential factor, and then we pay attention at the remainder of the division. If the remainder of the division is non-zero, then we move on and test the next number. Oh, does that suggest a loop to you? Because we're doing something repetitively. What changes between each iteration? In other words, the question is, if you compare two rows in here, what is the difference? It's incremented, exactly. So the potential factor is just one more than what it was before. Okay, that's kind of cool. How do we decide that we need to try another number, the next number, the next number, the next number? Okay, go ahead. The remainder is non-zero. Okay, very good. Because we can observe that the first time we exit the loop, 300 something, right, was when the remainder is 0. Okay, cool. That's one way to get out of the loop. What is the other way to get out of the loop? What I just said a little bit earlier? When the number that we are trying. Okay. So I'm going to show you at the beginning. So now we go like, okay, we have several pieces of things. So in this case, we say find prime factor f of n. If we find a prime factor f of n, then we say print f to the screen so that the end user can see that prime factor. And then we say n gets n divided by f. And we seem to be doing this in a loop here. So we'll just kind of go like, well, this is some kind of a loop, okay? So we just say it's a do loop. Because at this point, I don't know whether we should be using a pre-checking loop or post-checking loop, okay? So I'm just going like, yeah, it's some kind of a loop. But even if I just know it is some kind of a loop, we can still kind of comment on when do we get out? Exit when? What do you think? How should we code it? So getting back to the spreadsheet. So getting back to the spreadsheet, we got two ways to get out, right? But that's only for finding the factor. So once we have found the second factor, which is 2,237 itself, what happens to the number that I want to factor? It becomes 1. Because every time I find a prime factor, I divide the number to factor by the factor itself, and I keep doing this until it is 1, until the number that I want to factor is 1, right? Okay, so getting back to here, I just say when n equals 1. Okay, so let's look at this code here, and first of all, does it meet the rule of I don't want to deal with more than 6 things or 5 things at the same time? Yeah, I would say we got 3 lines that actually do something and an exit condition. So I think it meets that requirement. Second one, does it make sense? Okay, we plug in 20, okay, n equals to 20, and we go like, okay, what is the first prime factor f of 20? 2, okay, print 2 out on the screen, and then n becomes 20 divided by 2, which is 10, and then we check whether we should exit the loop or not. 20 equals to 1 is false. We should not exit yet. We go back to the beginning. So now we try to find the prime factor f of 10, because n is 10 at this point. We go like, another 2. Okay, so f is 2. We print 2 out to the screen, and then we say 10 divided by 2, which is 5, and then use it to update n. And then we get to the loop condition here. Does n equal to 1? Nope, not yet. N is 5 in this case. We go back to the beginning again. Then we go like, okay, find me a prime factor f of 5. Well, 5 doesn't really have any factor that in itself, so f becomes 5. We print 5 on the screen, and then we perform n gets n divided by f, but this time n is 5, f is also 5. 5 divided by 5 is 1, so n becomes 1. So by the time we get to loop exit when n equals 1, n does equal to 1 this time, and it's time to get out of the loop. Seems to be doing the job fine, right? Okay, then some people will say, but Tech, how do we exactly find a prime factor f of n? And guess what I'm going to say as a person with a P as the last letter of the MBTI type indicator? I'll say, we'll figure out it later. In other words, procrastination is not always a bad thing, because it leads to top-down design. Because you're just focusing on the big things, the big picture, and then go encounter one step, which is find prime factor f of n, and go like, we are running out of time today. We'll figure out next time. That essentially is top-down design. And no, I did not time my lecture like this. It just so happens that we are at the end of the lecture, and we are talking about how procrastination is actually a good thing when it comes to top-down design.